Okay. Any question about the previous session? In the previous session, we see NADE as an extension to fully visible sigmoid belief networks. Today, we want to suggest a general architecture for the density estimation. It means that in NADE we have just one hidden layer. As you see, we have a hidden representation X, and that was the result of an affine transformation and a nonlinearity over the inputs. So it is one layer. We want to extend it to a general case that you can have arbitrary number of layers, and that's the masked autoencoders for distribution estimation. You may remember the architecture of autoencoders. The architecture of autoencoders is an architecture which is usually used for unsupervised learning. As you see, you just have access to a vector X, and then using this architecture, this is a simple autoencoder with one hidden layer. You want to first generate a new representation for your data, which is called H, and then reconstruct your data using that hidden representation H. It is very similar to what we use for generative modeling till now. What is the similarity? What kind of similarity do you see between this architecture and what we talk about till now? The most important similarity is that in our case, for example, in NADE, and also in fully visible sigmoid belief network, we feed an input. And at the output, assume the task of density estimation. We estimate some lambdas. From this perspective, they are similar. Both what we talk about now, what we talked in the previous sessions, and this architecture accept a vector of dimension D in the output and in the input, and output a similar vector, similar dimensional vector in the output. In this aspect, they are similar because in the autoencoder you also input a vector of dimension, for example, 3, and output a similar vector. What is the difference? Why we cannot use? Why we can easily use this architecture instead of NADE? What is the problem? For example, instead of x1, here I estimate lambda 1. What happened? What is not met here?
I don't know. Maybe you're not passing modeling a probabilistic distribution.
What?
I'm not modeling a probabilistic distribution, rather it's doing a transformation.
No, there's something else. This x1 here is a function of which of the inputs? This x1. What? All of them. But lambda 1 should be rely on what? On nothing. Because lambda 1 is the distribution over the first random variable x1. And x1 is conditioned on nothing. So this is the main important difference. The autoregressive property is not met here. So based on the similarity, we want to change this architecture such that the autoregressive property is met. And then we can easily use this architecture as an architecture to produce for a generative task. So let's talk about autoencoder first. The autoencoder are very simple architectures. They apply an affine transformation over the input Wx plus C, and then I forget that sometimes a nonlinearity is also applied here. Sometimes always a nonlinearity is applied also to this affine transformation, and then the output is also an affine transformation of the hidden layer plus a nonlinearity that I forget here. So there is some challenges in training such architecture because it can easily learn the identity matrix here, but several constraints are added to the architecture so that they avoid identity transformation here. Because if the architecture has enough capacity, assume this is x1 till xd, and if it has enough capacity, for example, the hidden layer is also of the dimension d or larger, and then the output is also, we know that it is the same as input prime. It can easily learn to copy the first element in H1, and this weight would be 1, and all other weights would be 0, and it can easily copy each input in its hidden and then recopy the hidden in the output, and you have 0 loss while you have learned nothing. So they input some restrictions here. For example, the dimension here is much less than the dimension in the input, so that it is forced to learn something. So this is about the autoencoder. The loss are very similar to the ones you see before. For a binary autoencoder, you can easily use the cross entropy loss for each of the elements and assume them to be independent, so the total loss for the complete architecture would be this loss, which is the independency makes this summation. It is not a condition on anything. And also for the continuous case, also you can assume the output to be of Gaussian distribution, and then you have this loss for the resulting architecture for the continuous case. Okay. So we need something to apply autoencoder for generative model, and that's the autoregressive property. This is what happens when you apply the autoregressive property. Assume that this is the lambda 1, this is lambda 2, and this is lambda 3. And we know that lambda 1 should be independent of your input because it is conditioned on nothing. Just as a remember, we know that for a dimension 3 vector, we have this chain rule. And lambda 1 is in modeling the distribution over x1. So lambda 1 should not depend on any of the input. As you see here, this connection there is no connection here. Lambda 2 can only be connected to inputs coming from x1. As you can see, there is just one path here, and this path just is a function of just x1. And lambda 3 can be a function of x1 and x2, but it cannot be a function of x3. As you can see here, x3 has no output, so x3 is not used in any of them. So this is the intuitive way to transform an autoencoder into a generative model. Let's talk, and as you see here, this is exactly NADE. Okay, this is exactly NADE because it has just one hidden layer. This is exactly similar to NADE. So NADE can be tested as a type of autoencoder with some special type of connections.
Excuse me?
Yes?
For the autoregressive property, would you be able to define the autoregressive property by the line at the top with the model needing to generate in that chain kind of way? Or could you just reiterate what the autoregressive property is?
Oh yeah, the autoregressive property says that the distribution over your random vector can be factorized using this rule, chain rule. Using autoregressive property, you see that when you want to estimate the density over your first random variable in the vector in your sequence, it can be any of the, it's dependent on your sequence. It should not be dependent on any of the other elements in that vector. You see, because you don't see any x2, x3 here. Condition, assuming that you have access to x1 to calculate the density over the distribution over the second random variable, you can only rely on the first random variable, which is now in the condition. So this is the autoregressive property. You cannot have x3 here, for example. This is the autoregressive property. It's clear? Okay. Now we want to have an automatic way to design deep autoencoders to play a role of let's say, the generative modeling. We see that how we can transform an autoencoder with one hidden layer into a generative model, which is similar to NADE, but now we want to have an autoencoder with an arbitrary number of hidden layers. Assume that this is the autoencoder, and we want to say the procedure to design these connections. So first you assume an input ordering. For example, it is not necessary to have x1, x2, and x3 as your order. You can select any ordering in your inputs. This is for the case of a three-dimensional random vector. So in the second step, you set the output ordering as input. You see here. This is the input ordering. The first element is x2. So the ordering is written inside the neuron. You see, the x2 ordering is 1 because this is the first. X3 ordering is 2. It means x3 is the second, and x1 order is 3. It means that it is the last element in your order. You can easily select 1, 2, 3 as your order. That makes all the computation maybe simple. But assume that this is your order. The second step says that copy this ordering in the output neurons. 3, 3, 1, 1, 2, 2. You just copy them in the output. Then for each unit in the hidden layer, pick a random integer index from 1 to d minus 1. Then go through each of the layers, for example, the first hidden layer, and for each neuron, randomly select one integer from this interval. As you see here, for our case, we just have 1 and 2, because d minus 1 equals 2. So we should name each neuron with 1 or 2 in the hidden layer, both hidden layers, with the first and the second. Then this is the property that guarantees that the whole architecture preserves the autoregressive property. It says that each unit can be connected to the previous layer units with equal or smaller index in hidden layers, and a strictly smaller index in the output layer. You see that for the hidden layers, for example, this first hidden layer and second hidden layer, each neuron, for example, the second neuron, can be connected to the previous layers with lower index. This is lower or equal. This is 2, so it can be connected to 1 and 2. So it has both connection. It is connected to 2, it is connected to 1. And also this is 1, so it can only be connected to 1. It cannot be connected to the second ordering in the first hidden, in the input layer. And also these two neurons have the order of 2, so they can be connected to all previous less or equal than 2, and none of them can be connected to 3. Why? Why this neuron has no output?
Because it's higher than the
yes.
values of the upper layer.
Yeah, it is the last element in the sequence. And you see that x3 is not in the condition anywhere. So you do not need element in your autoregressive model. Because x3 is nowhere a condition. So you have no output connection from this neuron, because it is the last. You see that x1 is the last element in your ordering. It means that for this ordering, your chain rule says that for that ordering, it is P of x2, because x2 is the first element in the sequence. P of x, the second is x3 given x2, and the last one is x1 given x2 and x3. You are using this chain rule to build the architecture here. You can use any sequencing, but you assume here that the sequence is x2, x3, x1. And the last layer is more important. That in the last layer, you cannot be connected to elements with less than, let's say, ordering. It means that it is 3, so it can only be connected into neurons with index 1 or 2, which is connected to all of the previous layers. This is x1. It is connected to nothing. Why? Pay attention to this ordering. Excuse me. This is the first element in the ordering. I'd say x1 is not correct. This is the first element in the ordering. Why P of x2 is connected to nothing? Pay attention to this chain rule. Why? Because P of x2 is conditioned on nothing. At the output of this neuron, we have P of x2, and it is conditioned on nothing, so it cannot accept any input from the previous layer. If it accepts, it means that it is conditioning on something. Okay? And the second is just connected to the neuron with number 1. And if you inspect this architecture, you see that the autoregressive property can be easily verified in this architecture if you follow these rules. Okay, yes?
In the bottom layer from the, why 2 is connected to 2? Like the 2 should only rely on 1.
Yeah, inside the hidden layers you use them, but the most important point is the last layer, where the output neurons cannot be connected to input with similar number. Then you cut that path,
So why it's not the same? Because in NADE and in the chain rule, like 2 should only rely on 1.
Pay attention that we do not have any restriction over the hidden layers here. The hidden layers may, for example, 2 is connected to 2, which is to some extent contradict the autoregressive property, but pay attention that your output is not H. Your output is here, where you limit the connection of 2 to the previous 2, So in the output layer, you cut that path, and you do not have any path from 2 to 2 in the output. So if you follow the directions that are to this 2 number here, you can find just from 1. Here, because here you cut all the connections to previous layers number 2. You see here. So this is enough to have the autoregressive property.
So this architecture is only for density estimation. This is not for generation.
It can be used for generation too.
It's for generation, so 2 cannot be used for 2. Because
it can use. Assume that I use this architecture for generation. So for the first, for generating x2, what do I have? I have nothing, so I just have this neuron which is dependent on nothing, so I generate x2. Then what happened here? To generate x3 given x2, it is not needed to know these 2 elements. It is just needed to add your generated samples here and then calculate the middle layers, and then in the final layer you can easily compute this value, which is the probability density parameter, and then you can generate x3.
So like in the second layer for the two that is in the leftmost.
Yeah.
So that two relies on 1 and 2 in the first layer. So if you don't have 2, you cannot calculate the 2 in the hidden layer. You only have 1.
Yeah, but you know that at the last layer you do not need the neurons with number 2 to generate the parameter.
Exactly. So in the generation, the edges between 2 and 2 are not important. Layer, because you don't have 2, and at the final layer you don't even need that connection.
Let me talk about at the end of the class. I think you can generate samples without that connection. Thank you. Yes.
How do you decide ordering or input order?
That's really a challenging problem, especially for the inputs that are not ordered by themselves. It is sometimes heuristic, for example, for images, but for some types of inputs, for example, for speech, it is really chosen by the nature of the signal. Yes?
How did we decide the numbering in the hidden? Why is it 1, 2, 2, 1?
These are randomly selected. Yeah, these are randomly selected, but they cannot be changed during training. It means that you just select one and then freeze the architecture. Yes?
So with a standard autoencoder, you're not able to generate. With NADE, you can generate. If I'm remembering correctly from a previous course, you can also generate using a VAE. But VAEs don't have auto.
We will talk about VAEs. In the VAEs, you are that's something different. VAEs relies on another type of modeling, which is a latent. They have a latent variable, and their capacity is and their power is related to this latent variable. But here we do not have any latent variable, and it is to some extent more visible than the VAE. You will see that in the VAE you do not need any autoregressive property. It's based on a latent variable modeling. We will work on the VAE in the next model. You see, you do not need in the VAE to have the autoregressive property. And one important point that you can also consider the autoencoder itself as some types of generative modeling, and in the output you generate the parameter for the random variable. But you should pay attention that it is not an autoregressive because the property is not met. So,
Question.
yes.
As the input layer, the order goes 3, 1, 2. It's random, right?
Yes, it's not random, it is selected. It means that you have some intuition that this ordering may work.
Okay. And does the output also have to be the same order?
Yeah, the output is defined. If you define the input, the output is also similar as input. Yeah.
Okay.
Yes. Okay. Made some points about the MADE. In MADE, you can compute all the conditions needed to. One important point about the MADE and also other architecture we talk about in this till now is that they can be used to compute all the conditions needed to evaluate P of X in parallel. What does it mean? It means that it is in contrast to generation, which is a sequential process. It means that you should first generate x2 and then input x2, generate x3, then input x3, generate x1. For density estimation, for evaluating P of X means density estimation, you can easily put your input vector here and calculate all the parameters all at once in parallel. So the density estimation is in parallel. There is no limitation to have parallel computation here. You can easily compute all of the output neurons at the same time. Yes?
Can you quickly reiterate why NADE is not parallel?
NADE is parallel too. For density estimation, all of them are parallel. For generation, all of them are sequential. Yes?
On the previous slide, you said that the hidden layers are randomly generated.
The number inside the neurons, yeah, are randomly selected.
So, just in case, hypothetically, if all the numbers get 1, so we'll lose the X3 input.
Yes. No. X3 must be ignored here. You mean that this neuron?
No, if all the numbers of the first hidden layer are 1, randomly generated.
These are 1, yeah?
So the number 2, that is X3 will be
Yes.
So instead of random generation, shouldn't it be in some kind of a ratio or something?
Yeah, you can select, for example, half of them to equal to 1, half of them equal to 2. This is the approach they propose in their paper. Yeah, you can also generate, because there is no limitation in how you generate these numbers. Maybe they just find that random assignment may work better. Yeah. Sampling from NADE is sequential as NADE and as fully visible sigmoid belief networks. Assume the disordering, the chain rule is this one we see before. Because the distribution over X2 is unconditional, the second unit in the output layer has no input connection. It means this one has no input connection. And the last one, because X1 is in none of the conditions, the first unit in the input layer has no output connection that we see before. So this is the end of NADE. I was thinking about your question. I think to have the generation, maybe we need to limit the middle layers also be connected to less than. Yeah. We should check also, but I think it's needed. Yeah, because the next one are not generated yet. Yes. Thank you. Till now we see the autoencoders, NADE, and fully visible sigmoid belief networks. But you have also another networks that are in nature autoregressive. They are recurrent neural networks. To some extent autoregressive. This is a RNN, recurrent neural network, and as you see, the compact representation is something like this. And by unfolding, it means that you can have a sequence of different length and output the corresponding, the needed output you want. Maybe all of them are happening. For example, for sentiment analysis, you have just the last one. For example, you encode the information during the sequence, and then finally, and the output you infer about the meaning of the sentiment or the category of the sentiment. For example, in some application, like some types of, for example, in detecting the verbs in a sentence, you have all of these outputs. Each token in the input can be verb or not verb, so you have all of them. This is the architecture of an RNN, and one important point is that lambda 1 here is a function of which part of the input? Lambda 1, it is not related to x2, 3, or xl, but it is dependent on x1. You see the procedure, maybe I write it here, maybe I should. Yeah, the procedure is, as you can see, you initialize a hidden space H0, then this hidden space is multiplied by this matrix, the input is multiplied by this matrix, and in this unit they are summed together and pass through a nonlinearity and generate your H1. Here is H1. And then H1 is also multiplied by this matrix and generate an output. The output is passed through a nonlinearity here, which is sigmoid, because we are working on binary for example, random variable, and the output is the parameter for the first output in the sequence. This output is just related to the x1, and it is independent for the input sequences with the index more than 1. So there is some similarity between recurrent neural network and what we need in autoregressive models. What is that similarity? The similarity is the independency of this element from the a part of the sequence. But there is also a problem that lambda 1 is a function of x1. It cannot work because this contradicts the autoregressive property. Because in autoregressive property, lambda 1 should be dependent on nothing because it is the parameter for the first element in your sequence. For an RNN, assume I'm using an RNN for a verb estimation task. I have a sentence here. I'm going to bank. The label for the first element, this is x1. With some word embedding methods, you can embed this character into a vector, which is x1. The label corresponding to this element, to this input element, is y1 equal to 0 because it is not a verb. The second, the third is 1 because it is the verb, and the last, and these two are also not verb. So you have a label data set like this, and the label data set can have different length. This is one important point about the autoregressive property, about the RNN. As you see, NADE, MADE, and fully visible sigmoid network, all of them, the dimension of your vectors should be fixed and similar to each other. You cannot use images of different, for example, sizes in them. But here you can easily extend the concept to inputs with different dimensions. And it is the most important point about the RNN used as autoregressive model. So you initialize H0, and for the length of your array, you progressively update the hidden state and also calculate your output. These are very simple and can be seen in this architecture. What do I need to convert an RNN into an autoregressive, into a network with autoregressive property? I just need to shift the input one element into the right. You see, I just need to have H0, which is, I assume that is random initialized, and go and multiply by this matrix and go through a softmax. Assume that we are estimating a categorical distribution. And in the output, you have the parameter for categorical distribution over your first element. So as you can see here, the first output is dependent on no part of the input vector. So till now, we have the autoregressive property. Then you input your first element into this unit, and also this hidden layer with this matrix input to the hidden unit. And finally, you generate the parameter for the distribution over the second element. This is. So you can see here that O2 is dependent on just x1. You see, and nothing more from the input sequence. So we again have the autoregressive property until the end. At the last layer, you see, there is a problem here. This is x minus 1, one important point. This is x minus 1, okay? This is x minus 1, and here you have the same procedure to generate OL, which is the parameter for the distribution over your last element. Pay attention, this is XL minus 1. So again, OL is not dependent on the input sequence more than L. So you have the autoregressive property, and also you have the distribution over all the elements of your output. So by changing just by one place your input, then you can easily use an RNN as a generative modeling. This is, I call it generative RNN. Any question about generative RNN? Yes.
On the very top it says cat x1
Yeah.
given O1. What is it?
That's a categorical distribution. Yeah. A categorical distribution can generate the distribution over a output with some categories. Assume that they are more than binary. Yeah, ternary or more than that. Any question?
In the previous slides you were mentioning lambda.
Lambda?
Yeah, in the one before.
Here? Here I assume that we are exactly working on this example where the output is binary. So I just need one parameter because it's Bernoulli, 0 and 1. And in the case of the generative RNN, I assume that we are working on categorical with more than 2 categories, which is not binary. So we need a vector of length more than 1. So it can be used for a general case of elements with more than two states. Yeah. Yes?
So the RNN setting that the X are binary, that we generate lambdas.
Yeah. Here, for example, instead of O, we generate lambda. Yeah.
If it's the X is not a vector, it's just 0 or 1.
X, the input?
Yes.
Yes.
So it doesn't need the vector of W to be multiplied, just the W also should be like...
No, you can, for example, embed that one element into a higher dimensional space. Assume that we are... No, it is, assume that it is not word embedding. There are pixels of, for example, an image. You can multiply it by... you mean the embedding of this element in the first layer?
Can you go back to the slide that has cat and lambda?
Yeah, here.
Yes, here. So x1, xt, xl is binary.
The input is binary, okay.
So this wxh that is like being multiplied in x is should be a scalar value.
Why a scalar? They can be column vector. Assume it is a column vector.
Okay, so the column vector is just multiplied in a value which is
0 and 1, yeah. Yes. Okay. This is the procedure for generative modeling based on RNN. As you see, the H0. Any question? Yes.
How can it be used with different size of inputs?
Assume that exactly the ChatGPT. Assume the ChatGPT where you can use different size of the questions, for example. The most important point about the RNN is the parameter sharing. You see, independent of the length of the sequence, this model has no parameter other than the WYH, WHH, and WXH. It is not dependent on the length of the input. The number of parameters are just these 3 matrices. This is the simplest case. We have much more complex, for example, transformers or, again, architecture, decoder of transformer, I mean. Their decoder is save and preserve the autoregressive property, but in that case, you have a maximum length. Here, you do not even, you do not need to have a maximum length. Assume that I have two sentences. This is the first sentence that we have before the label 0, 0, 1, 0, 0, And the second, this sentence, 0, 1, 0. So to feed the first one into your model, I can easily start. Assume that we are in the RNN itself, because it is binary. It is not dependent on the case, because the second is length 3, the first is length 5. So I start to input I into this matrix, and after three calculations, I stop. Okay, and just the information between after 5, just the information between these outputs and your model. Assume that the model outputs 0.8 here. This is the output of your model, the lambda. This is, for example, instead of 0, because it is randomly initialized, it outputs 0.7. Here it outputs 0.2. Here it outputs 0.5. Here it outputs 0.4. So there is a distance between these two. You can update those 3 matrices using the distance between these two, for example, using a cross entropy loss. And after that, you update your list of parameters. Then again, you go through this sentence, and for example, instead of 0, you output something better than here. For example, 0.3. Here, for example, you output 0.5 and you output 0.2. Again, just for these 3 outputs, you again calculate the distance and backpropagate them through your 3 matrices, and all 3 matrices are updated. You see that, for example, this matrix, I assume that I have a length L. This matrix for the sequence of length L is updated just once, but backpropagating this error can be go through all of these units, so the first ones are more frequently updated. Is it clear? Okay. This is the procedure. Not many important points. Just to just know that O1 is independent of your sequence, and the last OI minus 1 is just dependent on the previous element in the sequence. Yes, because you know OI minus 1 is a function of HI minus 1, and HI minus 1 is just a function of XI minus 1 and previous. So you are generating the distribution over Xi given Xi minus 1 till the start of your sequence. Any question?
Just a question.
Yes.
Is it common to use RNN for image tasks?
Yeah, we have PixelRNN. One of the most well-known autoregressive models over images is PixelRNN. You can search that. That's a very well-known architecture using RNN over images. Yeah.
So how do you select the ordering of?
Yeah, it's hard, but and also in the generative task, for example, uncropping, it is very important how you select your sequence. Maybe some sequence works somewhere and some of them do not work. Yeah, it is a challenging task, but because the architecture was implemented in, for example, libraries, very easily you can use them. I think they are very popular in those days, but currently they are not used for images, and other ways, for example, variational learning are better options. So what is the pros and cons about generative RNNs? The first one is the variable length input can be handled, which is not the case for NADE, MADE, and fully visible. Second, the most important point is the fixed model size. It is independent of the length, and you just have 3 matrices, for example, in our simple case, but the model size is fixed. The history abstraction via the hidden representation. It means that if you progressively go through the model, you make an abstract representation for your history. Let's see here. All the history is encoded using this hidden layer. It means that all the information from the previous sequences is encoded in this one, in this representation, and that representation is used to calculate the distribution over the next one. So your path, for example, you are estimating xi given x less than I. It means that that hidden layer is just the path that you transferred your knowledge about the previous element in your sequence to your new random variable. And also the last one is present explicitly, here. Weight sharing is one of the most important features. Weight sharing is to some extent similar to fixed model size, because you share the weights, you have fixed model size, the W do not change during the sequence, and the cons are sequential computations similar to different, as you know here, even if the density estimation is sequential. Yeah. The most important point here, even the density estimation is sequential in contrast to previous architectures. If the length of the sequence is very long, this architecture may not work because you have limited capacity and it cannot handle the information through long sequences. And the ordering is also here required for your inputs. Yes?
Does weight sharing make it harder to train models?
It depends. As you see, weight sharing to this extent makes the architecture vulnerable to long sequences. Maybe if you do not have weight sharing, you have some better features for long sequences. It depends, yeah. But it makes the needed data to train a model with logical, for example, sequence very easy. And this is the result of PixelRNN we talk about. Assume that this is your input, and this is the original image. Input, the last column original, the first column is the cropped, and the task is uncropping, means filling the missing pixels. What can I do with an autoregressive model? The middle columns are the result of uncropping using a PixelRNN. But we just want to have an intuition how this task is done. Assume that the ordering, it is important to assume that the ordering is this way. I order such that before reaching the first element, which is missed, I see all of the part of the image which is visible. Okay, it means that all the upper half, I see all the upper half and reach the first missing pixel. So the ordering is selected in align with your task. Okay. What happened here? Assume that I am working in a density estimation task, okay? Because the first half of the image is visible, so I can start my computations until this point. Why? Because all the elements in the sequence are present, because the upper half is visible. So at this point, what happened? What do I have based on the information above? I can estimate the density over this new pixel which is masked. Do you agree? So I estimate the density over that pixel. For example, for each of the channels R, G, and B, I have one different one different distribution to make it simple. Maybe they use also the same idea, because considering all of them together is a large categorical distribution, 2, 5 to the power of 3, which is intractable to some extent. Assume that I independently generate the distribution over R, G, and B. So when I reach this point, I have 3 vectors, assume V1, V2, and V3. This is the categorical distribution over the R channel of the pixel. I have another categorical distribution over the G green, and the last one is over the blue channel. So we know that how to calculate these 3. Now I sample from them. I sample from this one, from this one, from this one, and generate a pixel, and put that pixel in the image. So I fill 1 pixel from the missing part. When I fill this element, assume that it is given to you. Then you can follow your procedure for the second one. Again, because this is given. As you may remember, I show this pixel with bar. Assume that this is P bar, your estimation, P1 bar. Then you can use the previous information and P bar 1 to estimate the distribution over the next one. And you can go through this procedure until the end of your image. And finally, you can see that this image is filled using. Why do I have different images here? Why do we just have one completion? Yeah, exactly. It is sampling. You can sample from this 3 categorical distribution for several times, and this result into different P bar 1, and again that affects the rest of your image also. And this is the power of generative modeling. You can fill the missing pixel with different different assignments. Any question? Yes.
So this ordering that you have drawn currently, so I expect that the last pixels are somehow independent of the actual pixel, not the masked pixels, because RNN is not able to remember all of the information they have, and the randomness can happen a lot, and then you need last pixels. Everything could be independent of the initial pixels, right?
Yes, to some extent you can see, for example, in this image, you can see the last part are to some extent not aligned in the compare this with the with your baseline. You can see that the last information are not very well modeled, it seems. Yeah, that's the case. And the things get worse when you assume that this half is missed, while your scanning is this way. Why? Because after having little information about the true image, you should estimate a new pixel. And when you have a large number of pixels scanned and then want to estimate the density over the new one, it means that you have a rich information of the content of your image. But when you face a new pixel which should be masked after a small number of visible pixel, it means that your information is not enough about the content of the image. And you cannot even go through for example, scan all of the visible parts when your scanning is in this procedure. So things get more challenging with these types of masks. Yeah, and this is the problem with ordering. If you use, for example, sometimes something like energy-based model, you do not have any of these problems. Yeah. Yes?
Could you please explain again how from one input these 7 are generated?
Yes. Assume that I have a trained model. We do not see training yet, but we see it hopefully today. I think the next was learning. Assume that I have a trained model over the visible, not cropped images, over the completely visible image like this. Yeah, I have trained the model, and then a new image is given to me. This is not from the training data set, and they ask me to fill this image. So I have a model. I have an autoregressive model with star parameters. It means that they are better, the best one. So what does an autoregressive model do? An autoregressive model starts with the first element and estimate the density over that element. Assuming we are in the density estimation mode. Density estimation. In density estimation, what do? We put the first element inside our model, then the second element, then the last element. But here we have all the information till here. Assume these are the visible pixel, and here I face a pixel which is masked. I call it P. What can I do? Because the previous visible elements are exactly the same as my ordering when modeling these images, I can easily use them because I do not need the rest of the image to calculate the parameter over this pixel, okay? Because my ordering is exactly similar to the way the image is masked. So what can I do? I can use the information here. Now assume that we are in a generation part. I can use all the information here to estimate the density over this pixel. I said that for simplicity, assume this pixel have 3 independent channels. It means that for now, we do not want to share information between R, G, and B. So it has a P1, P2, and P3. Each of them is a categorical distribution, and the autoregressive model can provide the parameter for that distribution for you. So I have the categorical over P1 given maybe lambda 1. These are the parameters, the result of model. The model give lambda 1 to me. And also the model give a distribution, let's call them R, G, and B. R, G, R, lambda G, and also a categorical distribution P of B given lambda B. So I have 3 distributions. And these distributions are such that a good combination of R, G, and B have a higher probability, you know, because you are in a model, and that model know that when the input in the first half are these pixels, it has an information what would be the probable next pixel. Okay. So when you sample from these 3 categorical distribution, you reach an R1, R, a G, and a B. And if you concat them together, you have an RGB pixel. Put this RGB pixel inside this element and call it P bar. This is the next element after the last seen or visible element. So after that, I come here. So if I have the visible side and also I have this field pixel, I can again do the same procedure for the next one until the end. So what happened? once I start sampling from them, I generate the second image. This is the second image, which is one sampling from this procedure. But if I repeat this procedure, because the output of sampling from this categorical distribution is not the same in the sequence of experiments, so I can see different pixels here. And then it fills the missing pixels based on the samples it generated. So different columns can be generated in this. Any question? Yes?
If at all I decide to leave the first 10 pixels as it is here and then I generate the 11th pixel, will the model be estimating it almost right, or how does it work if I still want to do that?
You mean assume I start with the first line?
Yes.
For the next one, which is also visible to me, I generate something.
No, whichever in the masked part. So I don't want to generate from the first pixel. Maybe I want to generate from 5th or 10th pixel.
Yeah, if you go progressively through the masked part, you use the all other generated samples, not one of them. Maybe I do not, if I understand your question correctly, it means that for these pixels, for this masked pixel, I just use this part and call it P bar. For the new pixel, I use both this part and P bar and generate P2 bar. This is P1 bar. And for this P3 bar, I also use P2 and P1 bar and also the visible part.
My question is, so is P2 closely related to P1? Can I generate P2 without? I'm just asking. I don't want to generate P1. And I just do P2.
What do you do for generating because to generate the parameter for P2, you need the information. You need the P1 because it is an autoregressive model, and autoregressive models assumes that to generate the parameter for this pixel, you need all the pixels before, and P1 is one of them. If you do not have access to P1, you cannot generate the parameter over the distribution. You know? Yeah. So let's talk about learning. We talk about different architectures and models, but we do not know yet how we can train these models. But because the training in these models is very simple conceptually, I put it here so we can share the information.
If cropping of the image happens not vertically,
Yes.
not below, but on the side, what is the difference between generation? Because you said that it travels horizontally first.
Yeah, you can either fill the image with these types of, let's say, mask, but the information, the most important point is that you may not see very good result as these results, you know, because when you start with this, assume that the scan is this one and the crop part is here. Starting from here, you can start generation for these pixels. So after that, you have again visible pixel, and it is not needed to generate anything. So your information is increasing here, but you have previously generated some pixels that may not align with the total of image yet. That may be a problem, yeah.
Can we do this process iteratively and get a better result? Let's say we did it once and then again started.
I'm not sure that because the point is not the, let's say, because low information here is the problem, and it does not change if you repeat your experiment. Yeah, the problem is the information which is here limited. Any question? Yes.
Let's say if we train the model on also rotated pictures,
in that case, it is important that in the training procedure, does the model see something like that? For example, rotated images that, and then you can fill them. If it see the such images, yeah, you can feel with that idea. Yeah. Any question? So till now, we talked about the model, and we have access to this set. This set can be NADE, made, fully visible, PixelRNN, all the type of architectures. Now we should define a distance metric such that starting from an initial point, for example here, if you initialize the parameter, for example, of a NADE, so you are a place in this subset, but that place is not a good place. So we should have a distance metric between the true data distribution and this point, so that we can minimize it and reach the point which is the most plausible point. This is our general view. So far, we talked about P and P theta. It means the complete family, the family, the model family, and it means from now on, we want to determine a distance and also optimize your model parameters to minimize the distance. One generic distance is KL distance. KL distance is the most generic metric to fit to distribution and to fit a model, and we see that KL have some properties. It is not symmetric and something else, but it is a divergence. It can define how far you are from your distribution. So assume that I design my distance metric as the KL divergence between the true data distribution and my model distribution, which we know that it is an expectation of the log likelihood ratio. It means that I should have access to the PDF of data. The procedure to calculate the density, the distance is this procedure. I should take the integral over the distribution of true data samples from the log likelihood ratios. This is the generic approach to calculate these are all vectors. To calculate the distance metric between your true data distribution and model distribution. What is the problem with this approach?
Not sure.
What? Why can I calculate this integral? Do I have access to this P of data? This is my objective. I do not have access to the true data distribution. This is my objective. I am designing a model which is similar to this data distribution. So I do not have access to the true data distribution. The problem is here. So we cannot estimate this expectation using the direct calculation. What is the alternative? We have an alternative. Yes.
Pull from the data distribution.
Yeah, and what do we call that?
Monte Carlo.
Exactly. We can use Monte Carlo estimation to estimate this expectation. How does that work? It starts by sampling from the distribution you are expecting with respect to that distribution, and then calculating the function, and then averaging over all your generated samples. So this is the original one. And also, we know that based on the definition above, if you are exactly matched your true data distribution, it means that your distance is 0. This distance can also be written as what we see in this relation. And one important point is that the first part important for us in terms of minimizing L of theta. No, because it is independent of theta. So I can easily omit the first term and start working on the second term. Working on the second term means that I should minimize minus expectation of this term, or equivalently, I should maximize, I omit the negative sign. I should maximize the expectation of log of theta of x with respect to data coming from your true data distribution. So these two optimization problems are similar. Okay. And this is the very, very well-known fitting or estimation model, which is maximum likelihood. What does it say? It says that your data distribution should be such that it assign high probability to data coming from your true data distribution. A good model is a model that maximizes this term. It means that assume that I start Monte Carlo estimation, x1 through xt. These are coming from P of data. How can I generate samples from P of data? Your data set are samples from P of data, because the data set samples are coming from the true data distribution. So I start to sample from my data set and call them x1 through xt, and then a good model should assign high probability to these samples. And it seems logical to some extent, because the samples want to estimate your true data distribution, so it should assign high probability to samples coming from that distribution. The desirable situation is when P of data assign high probability to probable regions in P of data. The important point is that we do not have access to P of data. And also one important point is that the maximum of this term. What is the maximum of this term? To know what is the maximum, we should pay attention to this equality. What is the minimum of L of theta? The minimum of any distance, we know that the KL distance can be 0 when two distributions match. So the minimum of L of theta is 0, and it cannot be negative. So the maximum of the likelihood of your model can be equal to this value. And this value has a definition, which is the entropy. It is not important for us, but just pay attention that it is the definition of entropy. Okay, so we can follow the next slide in the next session. Thank you very much. If you have any questions, we can talk. Thank you.